Good morning. Welcome to class Monday, April 27th. We're getting really close to the end of the year, to the AP test, about 2 weeks until then. It sounds like College Board is going to put something out. I thought it was the 28th, but it sounds like it's going to be early next week. They'll put in kind of a practice test. It doesn't sound like it's going to be so much a practice test where you can go through and it's really similar to the AP test. It sounds more like you're going to go through it and they might have a question and practice going through and turning things in. So as soon as that becomes available, I'll tell you and we'll go through that because it's really important that you figure out what the AP test will look like from a technical standpoint. So you know how you're going to have your setup, how you're going to go through it, how you're going to turn things in. So just keep an eye out for that. Any College Board emails you get, please read those and actually pay attention to them. If you still haven't gotten College Board emails and you can't find them, you really need to contact me. So you should have gotten a College Board email where they've been reaching out to you and been giving you links and then asking if you're going to take the AP test. That's really important because on May 14th, about 30 minutes before the test, so about 2:30 Central Time, you're going to get a link in your email which takes you to the AP test. So you need the link from your email address in order to actually take the test. So if you haven't been getting College Board emails, you need to either go to College Board and change your email address or talk to me or talk to the school, talk to something. You should be getting these emails. The other thing is just kind of try to catch up if you've kind of fallen behind, be turning in work. Big things to turn in are the tests. So you have the mock test to get turned in, and then the simple harmonic motion test. If you still haven't gotten that one in, get that in. I'll probably release the key to the mock test soon, and then you'll have to take an alternate mock test if you haven't finished that. So I'll definitely get the key out before your actual AP test, and you can go through and look at those. Yeah, other than that, just keep it up for a little bit longer, 2 more weeks for the AP test, and then we're kind of done for the year. And yeah, it really is your best opportunity to pass the AP test with just 2 questions. It really sounds like they're going to try to have a high number of people pass. It's kind of my opinion that, they're trying to justify that it's a good AP test, and part of it is going to be trying to get a lot of passing grades because, they're going to get probably hundreds of millions of dollars for the AP test like they always do. So it's probably in their best interest to have good grades. And so this might be the best year to take the AP test. You might be the most likely to get a really high grade. But that's just my opinion based on what I think. All right, so let's get to it. We have 3 of these more ranking tasks. We'll do more of these next class, and then after that, we'll go back to actual AP test questions that have been released, and we'll do that up until the AP test. All right, so here we have a figure. We have different carts moving at a horizontal direction at the speed specified. So we have 8 of these things. The cars hit and compress the springs to some maximum amount and then rebound. So they go, hit the spring, stop, and then bounce backwards. The springs are identical. So we have identical springs. They all exert an equal force on the carts, and the carts all hit the springs in the exact same way. Now, when they say equal force, obviously there's a little bit going on here, right? Due to, why am I blanking on the name? Hooke's law. There we go. The spring force is the spring constant times the displacement from equilibrium. So the force is going to be the same for each distance compressed, but obviously the force is changing as this compresses, right? As you compress more and more, you get bigger and bigger spring forces back. So all the carts hit the springs exactly the same way. The carts are not self-propelled, so they were pushed and they're moving at this speed along until they hit this. And then they compress the spring some maximum amount before stopping. And we want to rank the situations from the most time of compression to the least time of compression. So the time the cart takes to reach that maximum compression. All right, so first of all, let's just kind of start with what we have. What quantities do we have here? So what quantities, so we can figure out what equation or what concept we're using. Again, we're going to go through the explanation before we even get to the ranking. Okay, so we have mass. What else? Velocity. We have identical springs. So because we have identical springs, that means they have the same spring constant. And we're trying to rank times. So mass, velocity, and relating that to time. How do we do that? They also have identical forces. And then, like we said, it's not going to be a constant force because the whole spring force is the spring constant times the magnitude of displacement from the equilibrium position. You're feeling impulsive. Yeah, I would say feeling impulsive is a pretty good way to feel about this problem. Mass times velocity is momentum. Change in momentum is impulse, right? Momentum is mass times velocity. Change in momentum is force times time. Again, if you have your formula chart, write all over this thing, and this would be a really good thing to have in your AP tests. Like, if you don't remember delta P, write impulse next to it, things like that. If you lost your formula chart, I would suggest you print another one out and you write all over it. Or you could go in and open the PDF in a Word document and go through and change it up and then give yourself more space to write more about it. That would be a good way to do something. They should accept J. J is a really common way of using impulse. If you're unsure if they'll take it, just write somewhere J equals impulse, and then they'll definitely take it. I mean, you could go in and make up some random symbol and then do it, or say like Kasai, like some random Greek letter equals impulse, and that should be fine. The spring period formula, it depends on how you used it. It's going to be a little bit trickier there. It will, if it attaches, it will be a spring equation. But the problem is we're talking about, yeah, that's not going to work so much because we also have a velocity. So yeah, you're trying to use period of a spring. It's mass divided by spring constant. Yeah, that's not going to work so well. Yeah, because this doesn't really tell us distance. This gives us time. And we have they are going to compress different. Yeah, let's look at this. Let's actually go through these. So it really is trying to get us to use impulse with a mass and velocity. I'll put a pin in the period equation for now. So change in momentum equals force times time. Well, change in momentum is final momentum minus initial momentum is force times time. Again, if you're typing this out, you don't have to do the delta T. So the amount of time it takes to compress is going to be the final minus initial momentum divided by force. And again, we're trying to find the maximum compression. So at the maximum compression, this is going to stop. When we reach that amplitude, we stop. So we get negative mass times initial velocity divided by force. And we can't have a negative time. How this is going to end up working out is that whenever we collide with this thing, right, the impulse, the cart collides moving right, the impulse gets pushed to the left, and the force is to the left. So if I have a negative for my impulse, I'm also going to have to put a negative for my force. Otherwise, we're going to have a negative time. But because our impulse is pushing to the left and our force is to the left, these are going to cancel out. So I just have mass times initial velocity divided by force. Now, these all have the same force, so I don't even really have to rank the force. I really just need to rank the initial momentums. So same force, therefore we need to rank the initial momentum. So initial momentum for A, this thing has 2 kilogram mass moving at 8 meters per second. So this thing has an initial momentum of 16 kilograms meters per second. Initial momentum for B, 4 going at 8, 4 times 8 equals 32 kilograms meters per second. Initial momentum for C, 12 times 4. So this is going to be 48 kilograms meters per second. Initial momentum for D is going to be 4 times 6, 24 kilograms meters per second. Initial momentum for E, 2 times 12, 24 kilograms meters per second. Initial momentum for F, 6 times 8, 48 kilograms meters per second. Initial momentum for G, 8 times 6, also 48 kilograms meters per second. And the initial momentum for H is going to be 4 times 4. So 16 kilograms meters per second. So we're trying to rank this in the greatest time to reach maximum compression versus the least time to reach maximum compression. So greatest to least. And based on this, we're trying to rank our initial momentums. So the greatest time is going to be the most momentum, right? If I have a big momentum, it's going to take a lot of time. So I want a big momentum to take a long time to stop. So we have this. So the greatest time to stop is going to be the greatest momentum. Well, I have 3 that are equally big. So C, F, and G are the biggest. Those are bigger than my 32. So B is the second most time to stop. Then I get down to my 24. So I have D and E. D equals E. And then we're down to our 16s. Greater than A equals H. Did I miss anything? Nope. So that's why we're looking here. So we're ranking these based on momentum. So these are going to be different than if we rank these based on our masses. So let's think about what's different about this than just a simple harmonic motion back and forth using our period of the spring equation. So it seems like a good amount of people are trying to do this. Period of the spring is 2 pi times the square root of the mass divided by spring constant. So what? Yeah, why the period formula is going to give us something different. What's the difference between this period equation and this situation we have going on here? Because this period equation, it's really similar. You have a match attached to a spring, and then you stretch it out and you let go, and it goes back and forth a certain amount, right? So there's a few things about this period equation that are different than that. Is this cart just pulled back and let go and it's just moving back and forth attached to the spring? No. So that's kind of one of the differences we have here. Is it's just a cart moving at a certain speed, colliding with this. The other thing we're going to have is normally if we have a spring, it's just going to sit here oscillating back and forth. But here the cart is going to go compress and then launch back out, and it's going to keep going past. So it's not attached to this. So it's not fully going to be following this equation. Another place where this equation starts falling apart is this equation is for small displacements. So as we get to bigger and bigger displacements, this equation starts falling apart. But when we're looking at this equation, it's small oscillations and the mass is attached to the spring. If the mass can leave the spring, it's going to be a little bit different than this. If we're talking about a mass going colliding with the spring and then bouncing off the spring, anytime we're talking about the collision part, we're talking about probably momentum or energy. When we're using this equation, it's when the mass gets attached. So how I could ask a question like this where I would use this equation, it would be something like the car is moving along, it collides, and it sticks to the spring. And then when it sticks to the spring, it bounces back and forth as a single object. Is that one all right? And what's going to happen is you're going to lose some energy during the collision. And when that happens, then it starts oscillating. And then once it starts oscillating, then we would rank these by mass. So are y'all okay on that? It definitely makes sense why you thought to use that equation. But a big clue that they're trying to get you to use something different is the fact that they give you mass and velocity. So, hey, that's looking like momentum, and they're trying to rank time, and they say identical forces. That means probably looking at momentum. And then this equation here, we're talking about attached to a spring. So attached to the spring. So it would have to be attached to the spring, and you would use this equation either once it's attached to the spring or after it's attached, something like that, or if it starts out attached to the spring is where we would use that. All right. So if there's no questions on that, let's look at the next one. All right. So we have here shown below in a top view are 6 blocks sitting at rest on rotating turntables. All 4 of the turntables have the same rotation rate. The masses of the blocks and how far out from the center they sit varies. Specific values of the variables are given in the figures. Rank these blocks from greatest to least on the basis of magnitude of horizontal forces holding the blocks on the turntables. That is, first put the block that has the largest force holding it on the turntable, and put the last block that has the weakest force holding it on the turntable. So, how the turntables have. All right. So this is 89. So we're looking at our turntables here. So let's look at a side view. And let's draw a free body diagram. So if I'm looking at the side view, what forces are acting on these blocks? Friction. Which way is friction acting? Because friction is the interesting one. We obviously have our normal force holding it up and gravity holding it down, and these should be balanced on a flat surface. What is friction doing, and which way is it pointing? Yeah, it's pointing towards the center, and it's making this turn. So force of friction points to the center of the turntable, and it makes the block turn. So that means this is our centripetal force. So that means our force of friction causes the centripetal force. Now again, whenever we're labeling a free body diagram, centripetal force is never a thing we put on the free body diagram. Centripetal force is just not a real force. It's a force that's caused by other things. So anytime we have a centripetal force, it's always going to be something else causing it. It might be a tension making this turn. It might be a combination of tension and weight, or it could be frictional force. So the frictional force is the centripetal force making these things turn. I probably shouldn't even say causes the centripetal force. The frictional force is the centripetal force. So we're looking at this. Now, we could go, it is the frictional force causing this to turn. Let's look at our equation. That magnitude of frictional force is less than or equal to the coefficient of friction. So these are just sitting on the turntable. So this is coefficient of static friction times magnitude of normal force. Less than or equal to for this equation. So sitting at rest, same rotation rate. Less than or equal to. So they're being held in place on the turntable as they spin. So it's not sliding. And it's no mention that it's about to slide. So that means we're going to have to use less than. So it doesn't say anything about these are spinning at a rate where they're about to slide, or if they spun any faster, they would slide, or something like that. So less than here. That means we can't use this equation for frictional force, right? Anytime we have a less than, it's pretty much saying don't use this equation. So we can't use the equation frictional force is the coefficient of friction times normal force. That's my maximum possible frictional force. If this isn't spinning fast enough where it's about to slide, then we're below our maximum possible. So that means we're going to have to look at another equation. Well, we have radius, we have mass, we have the same rotation rate. So we have radius, we have mass, and they have the same rotation rate. So what are we ranking? What equation are we going to use then? Probably just going to be using our centripetal force equation. Mass times speed squared over radius. Now again, that's not on your formula chart. All you have is centripetal acceleration is speed squared over radius, and mass times centripetal acceleration is centripetal force, so mass times speed squared over radius. So you could write this next to your equation on your formula chart. All right, so we have these. Now, one thing here, same rotation rate. Does this mean these blocks are all moving at the same speed? No, they're not all moving at the same speed. What's the same? It's not the tangential speed that's the same, but they have the same angular speed. So they have the same angular speed. They're turning the same angle over time. But we want to get this to tangential speed, right? This is linear speed. That tangential speed is the angular speed times the radius. And again, the formulas that you really should put somewhere on your formula chart is that angular displacement is going to be radius times that, not angular displacement. So the linear displacement, or the distance traveled, is going to be radius times the angular displacement. And then that tangential acceleration is going to be radius times angular acceleration. These are equations that you should have somewhere on your formula chart, especially because you can use this on the AP test. All right, so tangential speed is angular speed divided by radius, or times radius, sorry. So we need to put this in here because I need to get rid of that tangential speed. They didn't tell us that they have the same tangential speed. So mass times angular speed times radius squared divided by radius. Mass times angular speed squared times radius squared divided by radius. R squared divided by R. Our centripetal force is just going to be mass times angular speed squared times radius. And sometimes you'll see this written as the centrifugal force. This is the equation for centrifugal force, which is a fictitious force. If you do more physics, you'll get more into that. So we can't leave it as just speed because these are at different radii, right? So these all have the same angular speed, but something going around the entire outside circle goes a longer distance in the same amount of time. So this is going faster. The ones in the smaller radius are going a shorter circumference in the same amount of time, so they're going slower. So this is why I can't just leave this in terms of linear speed. I need angular speed. When they said the same rotational rate, they're saying the same angular speed, rotational rate, rotation, angular rate, speed a lot of times. All right, so we needed to get this in terms of angular speed. Now we're trying to rank the things that are different. So angular speed squared is the same. So we're really only looking at mass and radius if they have the same angular speed. So centripetal force for A, well, mass is 6 kilograms times angular speed squared. Doesn't matter, it's all the same for all of these, times 2 centimeters. We should probably put that into meters, so 0.02 meters. They're all in centimeters. You didn't have to convert that technically, but I just can't stand not to. 0.02 times 6 is 0.12 omega squared. Centripetal force for B. We have a 4 kilogram mass, angular speed, 0.03 meters. So we have 0.12 omega squared. Centripetal force for C. It's a mass of 1 kilogram, angular speed squared, times 0.05 meters. So this is 0.05 times the angular speed squared. Centripetal force D is 5 kilograms, angular speed squared, 0.02 meters. So we have 0.1 times angular speed squared. Centripetal force E, 2 kilograms, angular speed squared, 0.03 centimeters. 2 times 0.03, 0.06 times the angular speed squared. And centripetal force F, 3 kilograms, angular speed squared, 0.05 meters. So we get 0.15 times the angular speed squared. So hopefully everyone got to this point. And again, if you're trying to rank things and you get to this point, you would have a decent amount of point that you realize that you're talking about centripetal force when you're talking about force holding it on the turntable, right? Um, the because whenever they're not being held on the turntable, it's because there's not enough friction and they're just going to keep sliding off forward. So if there wasn't enough friction, then this thing would just slide forward and launch off the turntable. So that's why we're talking about friction. And then the other important thing is realizing same rotation rate. Because they're talking about rotation rate, they're not talking about speed. So we can't say they have the same speed. In fact, they don't have the same speed. C and F have the... Actually, no, all the radii aren't different. Yeah, C and F have the biggest rotational speed. B and E have the second most rotational speed. And A and D have the lowest rotational speed based on the radius. All right, so we're ranking these from the greatest force holding them on. So the greatest centripetal force to the least centripetal force. So greatest is going to be F all by itself. Then we have A and B are the same. Then we have E. Wait, no, not E. Then we have D. Then we have E. Then we have C. And again, this year's AP tests, they're probably going to be trying to mix topics a lot. And this is a real easy way they can mix topics because we're talking about rotational motion and centripetal force. So we're talking about motion, we're talking about forces. Yeah, there's a lot of different things that we can talk about on this one. Questions on that? And by the way, these are the questions where physics gets really fun. Like you have, imagine an insect on that turntable, but the insect is walking. That's when it gets really fun, when you have the object that's moving. And so the turntable is turning and an object is moving on it. That's the really fun math, the really fun physics. No questions? Y'all are good? Everyone got this far? We're all able to make the connection that it's not linear speed, but angular speed? I'll take your silence as a yes. You fully understand this. I'm not delusional at all. If not, it's all right. This one was one that was a little bit trickier. I mean, we see on all of these that's kind of the difficulty in physics, is knowing where to start, knowing when to use, what to use. The difficulty on the first one, well, it seemed a lot like we can just use the spring period equation, when it's slightly different from that. This one, the easiest thing to kind of get caught up on is same rotational rates. They all have the same speed. And that's kind of what the AP test will do, how they start off, oh, we're just ranking the forces. Well, horizontal forces, well, we get to friction. Well, we can't use the friction equation because the blocks aren't sliding along the surface. They're stuck to the surface, static friction. So we can't use the frictional force equation. So we need to use our centripetal force equation because the frictional force causes the centripetal force. Then we have to get to the point where we realize, oh, well, centripetal force equation, same angular velocity, same rotational rate, but we want tangential, that translational velocity. And so we have to put the angular velocity in terms of the tangential velocity. And so there's a lot of small steps along the way. And honestly, that's what makes the AP test so hard. So if you're messing up along the way, don't stress out too much. I mean, there's a reason that these aren't simple. How many leaps that you have to make? You have to make like 5 or 6 different jumps and be correct along each of the ways. So, yeah. All right, last one. So we have seven different situations. Student is holding a meter stick at the left end, so at the very end at various angles. 1,000 grams, a 1 kilogram mass is hung on the meter stick at different locations. All the meter sticks are identical, but the distance along the meter stick at which the 1,000 gram mass is hung and the angles at which the student holds the blocks, holds the meter stick vary. Specific values are given in each figure. Ignore the mass of the meter stick. Rank the situations from greatest to least on the basis of how difficult it would be for the student to hold the meter stick from the left end of the position shown. That is, first put the situation where it'd be the hardest to hold the meter stick at the angle shown, and put the last situation where it'd be easiest to hold it at the angle shown. All right. So what are we ranking here? What's making it easier and harder to hold these things? Torque. Yeah, it is definitely going to be torque. So I'm going to start by looking at forces, though. So you are 100% correct. It will be torques. When we look at forces, how much force is the person holding up every single time? Well, they're holding up the weight of the meter stick plus the weight of that 1 kilogram mass. So every single time the person is holding up, we'll call this it's just the weight. Every single one of these are holding up the same weight, right? So that's our kind of indicator we're not looking at weight. So every single one of them, they're holding up the weight of the meter stick, and they're holding up the weight of the object itself. So we're not looking at just them holding up the weights. So we're really looking at torques, how much torque they're having to provide to hold this up. And they're all holding this relative to the endpoint. Yeah, the weight of the stick, I don't think it ever explicitly says that it's nothing. We're going to see it's probably going to be less than. Where does it? Oh, ignore the mass of the meter stick. There we go. I can't read. So yeah, the meter stick has a negligible mass. So we're looking at torques. So torque is radius times force times sine of the angle. And again, angle between radius and force, and all of these are forces of gravity, weights. All right, so we're trying to rank torques. Now we hold these from the same end at every time, right? So that means we're not changing where we hold it. So a bigger torque provided by the mass is going to make it harder to hold this up, right? So bigger torque equals harder. So more torque by the 1 kilogram mass means it is harder to hold up the meter stick / mass. All right, so let's look at A. I'm going to draw each of these out. Again, whenever we have rotational motion, a lot of times it's really important to draw things out. So I have my radius right here. That's the meter stick is my radius. I'm holding this right here. This is my pivot. Right, my hand is where this is trying to pivot about. And then I have the 1 kilogram mass hanging down here. And I'm given this angle is 30 degrees. All right, so I do my torque. My torque is radius times force. So it doesn't give me a radius, but if we notice, a lot of these give us some amount of length. So I have like E is 3/4 of the length, G is 3/4 of the length away. So let's just call this length L. So L is going to be the radius to the mass. Then I have the weight of the mass, which is 1 kilogram times 9.8 meters per second squared times sine 30 degrees. Now, I messed up something there. What did I mess up? So I messed up something and I assumed something that's not always going to be true. Well, I'll tell you the thing I assumed. I assumed that this tension force here is equal to the weight, which meant that this force here, because really this force holding this down is tension, right? So in reality, when I put this into my equation, it needs to be tension, not weight, right? It should be length times force of tension times sine of the angle. But because this is just sitting there at rest, I can do length times weight times sine of the angle, as long as this is not accelerating. Or here, we're just holding it and it stays at rest. So that is a big thing that we need to make sure. So the holding the meter stick, they don't necessarily explicitly say holding at rest, but if I'm holding something, that's normally kind of implying I'm not doing something to it. If I just say holding, if I meant rotating, turn, they would say something about that. So just to hold it in place without accelerating. So that's the first big thing. Because this is held in place without accelerating, my tension and weight are balanced. Zero acceleration, no net force, so I can use weight as my tension. Remember, this is very different than the situation where we have like a mass hanging here, like that, right? In this situation, we would have weight is going to be bigger than tension. So in this situation like this, we can easily have tension does not equal to the weight. All right, so that's the first thing to think about. We can only use weight because we're not accelerating. Otherwise, we have to use tension, and it's a lot messier to get what that tension is. The other thing I messed up, no one knows, no one sees, but it's the angle between the force and the radius. Did I use the angle between the force and the radius? I did not. I used 30 degrees. That is not the angle between the force and the radius. I need the angle between the force and the radius, right? So I need to use this 60-degree angle. So 60 degrees. And I'm not going to bother with sine 60 being square root of 3 over 2. Let's just evaluate that. 9.8 times sine 60. You could just use square root of 3 over 2 times 10, just approximate g as 10. Would have also been fine. But the torque for A is going to be 8.49 L. Right, no questions. Everyone's okay with those? Angle between the radius and the force, not always the same as the angle given. All right. Again, these are a few things that could really easily mess things up. They give you the wrong angle, or the system is accelerating, and when the system accelerates, I can't use this equals this. Just a few things I could easily change about this to make it a much more difficult question. All right, so B is really similar, except a little bit easier because I have the masses right here. Distance L over 2. Still a 1 kilogram mass hanging straight down, so that means the angle between the radius and the force is just 90 degrees. So the torque by B is only L over 2, right? My hand, my pivot is only L over 2 from where the force acts, times 1 times 9.8 to get my weight, times sine 90. Sine 90 is just 1. Again, if you forget that, you just have this. Sine 90 equals 1. Or use your calculator. If you don't have a working calculator or something that you can use, it would be good to reach out to me and we can try to figure out something to use. 9.8 divided by 2 is 4.9, so I have 4.9 L Newton meters. All right, torque C. One kilogram. Again, they give us the wrong angle here. 30 degrees right here. So we really want this angle here, the angle from here to here. So what's that angle? Not 120. Hey, yeah, actually, it is 120. What am I saying? Yeah, sorry. Blank there for a second. Yeah, so if I made a parallel line here, this would be 30 degrees. This would be 90 degrees. 30 degrees plus 90 degrees equals 120. Sine 120 degrees. 9.8 sine 120. So we get another 8.49 L. Which, again, is kind of straightforward from here, right? Because holding it up 30 degrees is the same as holding it down 30 degrees. The hardest way to hold this is with it straight out like this at the very end. But if I lift this up a little bit, its torque is less and less. And then when I hold it like this, then the weight is straight down. It's not trying to turn it, not providing a torque, so that's the easiest to hold. Or if I hold it straight down, the weight is straight down and I'm not trying to hold this up, keeping it from turning at all. So as I get closer to vertical, either up or vertical down, it's getting easier to hold. And then up 30 degrees is going to be the same difficulty as down 30 degrees. So that's kind of matching an intuition that some people probably had. D. No, I'm holding this up at 45 degrees. Can I use 45 degrees as my angle? Yeah, I intentionally asked that to try to get you to say the wrong thing. But yeah, we can use 45 degrees, but not because that's 45 degrees, only because this is 45 degrees. I was trying to mess with you to say no, that you can't use the 45-degree angle. Didn't work. But yeah, so we can't use that 45-degree angle, but we can use this 45-degree angle. We have a 45, 45, 90 triangle. So the torque by D length times the weight is 1 times 9.8 meters per second squared sine 45. Again, we can do sine 45 squared of 2 over 2. I'm just going to evaluate that. So 6.93. E is another easier one because this is just straight down at 90 degrees, or only at 3/4 L. So torque at E, 3/4 L times 1 times 9.8 times sine 90. Sine 90, just 1 again. 3/4 9.8, what is that? Like 6.7 I'm blanking. 9.8 times 3 divided by 4. 7.35. 7.35 L. And you don't even have to put this in because we have the same mass. We don't even have to calculate this. We really only have to calculate the radius times sine of the angle. F. Now it's at the very end. And this is going to be the hardest one to hold up, because the entire length L and at a 90-degree angle, so the torque F is going to be by far the hardest. L times 9.8 times sine 90. So 1 times 9.8, we have to hold up all 9.8 L. The farther we are away, the harder it is to turn, or another way of thinking of it would be a bigger moment of inertia, harder to turn at the very end. A few ways to think of it. And then G, we're 3/4 L away. And then we have another one where we're given this angle is 30 degrees down. Well, we already did one with a 30-degree down angle. That's just going to be 120 degrees. Torque G, 3/4 L times 9.8 newtons times sine 120. I'm just going to calculate this. I'm doing everything else. 3 divided by 4 times 9.8 sine 120. And we get 6.37 L. I think this was probably the most straightforward out of the ranking ones. Probably the biggest mistake people would make is using the incorrect angle. And a lot of people probably automatically assume tension equals weight, which worked here. But again, don't always assume tension and weight are equal, only if the thing is at rest, staying at rest. All right, so we're trying to rank from hardest to hold to easiest. So hard to easy. So the hardest is going to be the biggest torque. Again, make sure you put this into words. More torque makes it harder to turn. So the most torque is going to be F. So 9.8. And then we had two 8.49. So A and C were equally the next most difficult. Then we had a 7.35. So F was... What am I saying? Where did I mess up? F. That's an E, not an F. There we go. E is next hard. And then we have a 6.39. So D is next. Then we have 6.93. Then we have G at 6.37. And then finally, the easiest to hold would be B. A and C. A equals C. That's what it is. A equals C, not A equals B. I swear I can read. All right, so if you have more questions, feel free to stick around and keep asking those, but I'm going to wrap up this video to keep it from being too long. So again, next week, a big thing, College Board should be putting out a practice test. It sounds more so it's like it's going to be practice for the formatting of the test, but they might give you actual practice test questions. I would say take those seriously. The other really big thing, make sure you're actually getting College Board emails. If you're not getting College Board emails, you need to tell me immediately, so we can figure that out and change it to where you are getting the emails. Otherwise, you won't be able to take the AP test. And just if you haven't already, finish up your mock test and your simple harmonic motion test so I can actually get those graded and get the keys out. But other than that, have a good day.